Log on, tune in, find out. Another good idea from Cambridge.
PDAs in kinetic theory. We are very pleased to have two very, very prominent speakers here today. The first one is going to be Tai-Ping Liu from Stanford, and he's going to talk about Hilbert's sixth problem.
Okay, thank you. I'm going to give this talk with this big title, and I know I should not be the one to give such a talk. Even though I have worked on this field for 10 years, but 10 years is a very short time for me. And turn the microphone up. Okay, so I've been working on this field of bottom equation for 10 years. 10 years is a very short time for me. On the other hand, anybody in a good position should give such a talk, because this is an awfully important problem. And maybe it's good for me to give a talk, because I haven't learned enough to have a good sense of what is appropriate thing to say and what is not appropriate thing to say. Okay, so here we go. So this is, let's take a look again of Hilbert's original writing. Now, there are people who say that because Hilbert is thinking of probability, therefore Hilbert's sixth problem has been solved by Kolmogorov and others. But if one look at this thing, I think it's fair to say that Hilbert was thinking of a kinetic theory of gases. I think that's also a lot of people's understanding. But the title is so big that there are people who say that, well, if we talk about axiom of physics, then one could think about quantum field theory and so forth. I think a lot of people actually think about Hilbert's sixth problem in terms of quantum field theory. So we think about kinetic theory of gases. Now, there are several, as we know, there are several problems in his 23 problems that is of a general nature, and this is one of them. The last one about calculus variation is very general, and there are some specific problems like formula theorem. But this is a general problem. I was told that when Hilbert drafted these 23 problems, he got quite a bit input from Minkowski. Now, this problem, I like to believe that it's very much Hilbert's problem, in the sense that Hilbert must be thinking about, because you know Hilbert did say non-Euclidean geometry, the axioms, and but I was thinking more in terms of say Weierstrass and Hilbert, this Dirichlet principle that Hilbert really nailed it down exactly, completely. So I have been talking to various people, and I think there's a general understanding that the Hilbert sixth problem, because it's talking about axiom of physics, it's not purely analytical. It involves also the formulation of the problem based on physics and formulated mathematically. And so let's try to think this in this sort of mode of Weierstrass, Hilbert, how to formulate the problem going from Newtonian physics, then Boltzmann equation, and then fluid dynamics. All right, so let's move on. This is the kinetic theory. I don't think I need to introduce this, but let me nevertheless go through it quickly. C is microscopic velocity. That the inclusion make it a kinetic theory, and the macroscopic quantity such as density, you have to integrate this with respect to all the microscopic velocity. And the same with momentum and energy. Energy has two parts, internal energy and the kinetic energy. If you find this distribution function f as a function of space, time, and microscopic velocity, then you can compute all the macroscopic quantity you need. Okay, these two are particularly important. The stress tensor, which is computed as the flux of the momentum, so that's give us the stress, and this is the flux of the internal energy, and this gives us the heat flux. So there are these quantities which one can compute if one knows the distribution function. So fluid dynamics, let me just remind you that the Navier-Stokes or order equation, it is the equations for this variable on this side. The kinetic theory and the fluid dynamics are related by taking this integral, which Hilbert said the mean values. Another thing about the difference between fluid dynamics and the kinetic theory is the boundary condition, and that's a very essential part of that theory. The fluid dynamic boundary condition, there are the Neumann type for order equation, for example, Dirichlet type for Navier-Stokes equation, or you can have a Robin type like Navier boundary condition, but still very limited. And also the coefficient to determine Navier boundary condition, for instance, is ad hoc. However, for the kinetic theory, one can have it a more first principle basic assumption on the boundary condition and derive the fluid dynamic boundary condition from those basic boundary condition on the level of kinetic theory. So this is the part that people pay a lot of attention to when one want to relate the kinetic theory to the fluid dynamic. So here is the bottom equation, and I'm taking this notation as usual. So here is what happened to that equation. There's the collision operator. This is the gain part, that's the loss part. So here's the picture. If you have a velocity, say C star, and go to something else, then there's a loss term. And there's velocity C star prime, and if it's produce something, say C, and something else, then this is a gain, because C is the one that we monitor. Now, in the formulation of bottom equation, this is all importance product, which means that the velocity distribution before the collision are independent, and the same with here. The velocity after collision is not independent. These are the things that we all know. At the bottom, I write down this cross-section B here if it is Haas field model. Now, the bottom equation consists of two parts. One part is transport. So this monitor how much material moving with the velocity C as you move with the material. Okay, so that's the rate of change if you move with the material. And the changes because some of the particle move with you, collide with other particle and gone, and it is this turn. As you move along, particle with different velocity collide and become with the same velocity as you and join you, and that's the gain part. Okay, that's the gain part. And so that's the collisional gas dynamic. And immediately you see that this equation is reversible, because if you change x to minus x, t to minus t, this side changes a minus sign, but this side does not change. So the equation changes, and therefore it is not reversible. And the reason is simply that the collision is assumed to occur very, very locally, okay, unlike the Vlasov equation. Now, another thing which everybody pay attention to is that the collision is only binary, and that's because we are in the rarefied gas regime, and the gain part and loss part are product, so which is related to the fact that you assume the gas before they collide are not correlated, and therefore the chance for two particles distribution is a product of one particle distribution, the independence. Now, all these are supposed to be derived from the Newtonian system under so-called Boltzmann-Grad limit, which is the following. You have n, which is the number of particles in this room with 10 to the 23. Okay. And d is the diameter of the particle. And you take n to go to infinity, d to go 0, and nd squared fixed. So that's the Boltzmann-Grad limit. And supposedly, at that limit, assuming certain things about initial data of molecular chaos, then you get this equation. Okay, there's a lot of if. And one of Hilbert's 6 problem, maybe the most important one, is to make clear what are those if, and then prove a theorem for the then. Okay, so let me start with two fundamental fact about Boltzmann equation. One is that the collision operator will change the distribution of the particle in their microscopic velocity, but it does not change the number of particles, it does not change the momentum, does not change the energy. So which means that if you count the total amount of collision integrating with respect to microscopic velocity is 0. So it does not create the material. It does not create the momentum, does not create the energy. So that's the conservation law. And that's the H theorem, which says that if you multiply by log f, then the right-hand side, the collision part, will be less than equal to 0. Okay, so I should go quick on this thing. Everybody knows this. So the conservation law, which is this: if you multiply the Boltzmann equation by 1 kc half kc squared and integrate the Boltzmann equation, then you get this version of conservation law and H theorem. Now, H theorem, as we all know, it says that the derivative of something less than equal 0, which means it's some kind of gradient flow, and therefore it is a quantitative way to say that Boltzmann equation is not reversible. So this is also, I think, familiar to a lot of people, but nevertheless, let me repeat it. There's a paradox and controversy of deriving the Boltzmann equation from Newtonian particle system. First, Poincaré has a recurrent theorem which says that if you start with a state space, which means that you have a particle and the velocity prescribed, a bunch of them. So this is a system. And as time goes on, almost surely you go into any smaller neighborhood of the original state. If you exactly go to the initial state, there will be periodic solution. But that, of course, hardly happen. But you go back to an arbitrarily small neighborhood of original state if you wait long enough. Okay, that's why the Poincare recurrence theorem, and the time you need to wait is the Poincare recurrent time. The Boltzmann equation, which is derived from a Newtonian system, and for which the Poincare recurrence theorem applies. And so therefore, there's this paradox. The Boltzmann equation is not reversible, and yet Poincare says that if you wait long enough, you come back to a small neighborhood of initial state. So H theorem says that something keeps going down. Poincare says that if you are here, you eventually go back somewhere here. Okay, so that's a contradiction. However, Boltzmann is very, very clear. He said that this description of Boltzmann equation is much earlier in time scale than the Poincare recurrent time is. Or in other words, if we take the Boltzmann graph limit, then the Poincare recurrent time is pushed beyond infinity. Okay. But all this needs a proof, and there's a proof in a very limited situation by Oscar Stanford. So let me go through that very quickly and comment on it a little bit. So we start with Liouville equation. There was an article in last year's Physics Today talking about Liouville equation and all this state space, phase space like that. According to the article, Boltzmann was the one really has all this concept right, the phase space, the Liouville equation, and so on. He needs this because he started with that. So he established this theory, actually. All right, so this is n particle. Fn is the distribution of the n particle. The first particle at the location x1 with velocity c1, and second particle located at x2 with velocity c2, and the distribution is called Fn. And you can take a marginal probability, integrate all the other thing out, which means you don't care what is the second, third, and nth particle. So what are the distribution, the probability density of the first particle, and that you call F1. And your F2 would be the distribution of the two particles, the first particle at x1, the second particle at x2, and their velocity are c1 and c2 respectively. So the Liouville equation here, you can integrate with respect to the remaining variable, and then you get these equations. The first equation is that F1 will depend on F2, and the second equation is for F2, which depends on F3. Okay, that will do. So you have 1 depend on 2, and the 2 depend on 3, and 3 depend on 4. So this is a familiar sense in such a situation, and that's a closure problem. Okay. I'm writing this for a particular situation, which is called a radial cutoff, which means that the force between the particle are zero outside a region. Okay. In fact, it is a major open problem if the force is not finite range, how to derive Boltzmann equation. This remains an important open problem. So Harold Grant write down everything precisely and derive the Boltzmann equation for the finite range force, assuming that the initial the solution itself satisfies molecular chaos assumption. Or this molecular chaos assumption assuming for the solution. Okay. Then Oscar Stanford, in this famous paper, perhaps the most important paper mathematically on Boltzmann equation, he showed that for a very short time, the Boltzmann, if you assume initial data satisfy the molecular chaos assumption, then in the limit you get the Boltzmann equation for a very short time. There was a meeting 30 years after the publication of this paper, and Oscar Stanford corrected the general misunderstanding. He said that the time for the validity of his proof is not 1/3 the mean free time, it's 1/5 the mean free time. Okay. Now you can find the proof in this standard book, textbook. Now this is proof by comparing the BBGKY hierarchy that I wrote down before with the Boltzmann hierarchy. Boltzmann hierarchy, you can just cook it up, okay, assuming the product rule. And the assumption is that it's the product, okay. Now, let me comment on this proof because this is such an important paper. The proof is of Cauchy-Kowalewski type. And you need to know F1, F2, F3, all the hierarchy up to infinity. Okay, it's just like a Cauchy-Kowalewski theorem. You need to know the function, its derivative, second derivative, third derivative, all the way down. Okay. Now, Cauchy-Kowalewski theorem perhaps still is the most important existing theorem in PDE because whenever you don't know what to do, you go back to Cauchy-Kowalewski. Okay, all the other smart things may not work. Okay, but this is you can count on. However, because using the Cauchy-Kowalewski type of analysis, this make the estimates and so on very, very rigid. And right now, you can do it up to 1/5 mean free time, which means that hardly there's any collision at all. Okay. But still, this is a great result. Now, the open problem here is that to show that it propagates for any positive time, at least for as long as the Boltzmann solution exists and smooth. Okay. And there's a lot of theorem about the existence of the smooth solution for Boltzmann equation. Of course, this is the famous differential. But let's look at a more restricted case of the smooth solution of Boltzmann equation. And one would hope to be able to prove this limiting result for that regime. And that is perhaps the most important open problem. What one needs to show is that the molecular chaos hypothesis persists at all the later time in that limit. Now, if you look at Oscar Stanford's proof, it's so wise that he did not really have to confront the combinatoric reasoning about why molecular chaos assumption should persist. Okay. My 2 cents is that maybe we need to confront this combinatoric problem. Another open problem behind this is that, well, okay, why there's a combinatoric analysis that ought to be there to show that the molecular chaos hypothesis is persist and more so as n go to infinity, d equal to 0, and d square fixed. Why? Well, that's because the collision mostly are binary. And as far as the binary collision is concerned, it is a very small portion of the total collision. And therefore, in spite of the fact that 2 particles interact before collision are independent, and after collision they are correlated, and yet when the particles interact again and again, every time when they collide, they are independent. Why is that so? Well, that's because it's verified limit. But another problem behind this reasoning is that why, if that is so, and you can prove that theorem, then there's an H theorem. But H theorem comes on the collision, and comes on the fact that after collision they are correlated. Suppose that if the particles after the collision are still independent, assuming that, then it's very easy to see that this collision operator Q is identical to 0, and they would not have H0. Okay. All right, stop there. I'm sure I have completely confused you, and that's what's meant to be. All right. There's a certain, I don't know how to put it, okay. I thought there's something to that. All right, another thing is that in the derivation by Hilbert, let's forget proving the fact that molecular chaos assumption persists at later time. Let's assume that. Okay, let's assume that. Assuming that there's still the formal derivation of the bottom equation from Liouville equation, and that was done by Hilbert. I think Boltzmann basically had that. But that was done when the force has finite range. Of course, the force may die down quickly over some distance, but to assume that the force is finite range is not really physical. And there's a so-called infinite range collision operator, but that was not that was sort of, you look at the binary collision 2-particle system and just stuck into that B. Okay, it was not honestly derived. This is the part I would like to repeat here. In solving the Hilbert 6 problem, it is not just to solve some open problem. It is also need to formulate that problem based on physical principle, and that the second problem has not been done even on that level. Okay, so this is about from Newton to Boltzmann. Okay, and let me see. Okay, I'll be okay. Now let's go to from Boltzmann to Euler, or to Navier-Stokes. So here's the H theorem, and as we all know, this will keep this H theorem say that something keep going down. Something keep going down because the derivative is less than or equal to 0, but it stops only at the state when the distribution is a Gaussian in this microscopic velocity. So this is a Maxwellian state. Assuming that, and then this is the conservation law. Now this conservation law is not a self-sufficient partial differential equations because there's 1, 2, 3, 4, 5 equations. And there are 5 unknowns here, 1, 2, 3, 4, 5, but also this unknown p, which is a symmetric tensor with 6 parameters, and q is 3. So altogether, there are 14 unknowns here for 5 equations. They are the second moment or first moment of Boltzmann equation. So Boltzmann equation actually is only one equation, which is very nice. But if you want to relate to PDE, actually it's not this PDE, because this PDE is not self-sufficient. It is related to, in a way, infinite number of PDE. However, if one assumes, which is hardly ever happen, assume that F is a Maxwellian, meaning that it's a Gaussian in the microscopic velocity, then you get all the equation in gas dynamic. And that is a 5 equation with 5 unknowns, because the pressure now will be just a product of density and internal energy. And the heat flux is gone. The stress tensor is only pressure. And this is easy computation. One show that. Now, the relation of the Boltzmann equation to fluid dynamics has been done, and that was done by Hilbert and by Chapman Enskog. And what happened is that under certain assumption, a certain limit, you get all the equation. In that case, the stress tensor is a scalar, just a pressure, and the heat flux is 0. And the Navier-Stokes would say that the stress tensor is the gradient of the velocity. And the heat flux is a scalar, the heat conductivity times gradient of the temperature. So that's a Navier-Stokes equation. Here's one open problem. This open problem is not it's the immediate open problem you can think of, though may not be the first thing you should think of. For one thing, it may be not interesting for your consideration, and besides, this is a very difficult problem. Okay. So if you take k go to 0, if k go to 0, you expect q to go to 0, and we know that q is 0 when f is Maxwellian, so you expect f to go to Maxwellian. But if f is Maxwellian as k go to 0, then the Boltzmann equation is equivalent to the order equation in gas dynamics. So the problem, the open problem, is to show that. But the difficulty is that as k go to 0, q may not go to 0. Why? Because this side may not stay bounded because of shock wave. And if there's a shock wave, then the shock layer, along the shock layer, the derivative will go to infinity of the order of 1 over k. So in other words, the most you can hope for is that f will go to local Maxwellian outside the shock wave. But shock can be dense everywhere. So the most you can hope for is that you go to local Maxwellian almost everywhere. And yet, the solution should go to the weak solution, the entropic solution of the order equation. So that is the open problem, which is, as I said, I've warned, this very difficult problem. The shock wave is a strongly nonlinear object, and you need a strongly nonlinear analysis. So I want to go into this subject a little bit. About the shock wave, there's a paper by Kevlis and Nikolenko, and Shixian and I has also worked on that. What they did is use the Navier-Stokes equation, compressed Navier-Stokes equation, and do Lyapunov-Schmidt reduction. I was talking to Ross Keflich actually that was so many years ago. He come to Maryland for a job interview, but he chose to stay in Quran. I was in Maryland that time. Anyway, okay. And he told me that this is a positivity of the Boltzmann shock because you see in the Gaussian, the Maxwellian distributed exponential decay there, and any perturbation by the Lyapunov-Schmidt will upset that. Okay, so may not be positive. So 实现呢, that's our entry into the Boltzmann equation, try to prove the positivity of Boltzmann shock, and we did that. But there's a monotonicity which we could not do, and we did that only very recently, and in our study of invariant manifold theory for the steady Boltzmann equation. Okay, so there are some results on Boltzmann shock, just a traveling wave. Okay, one shock. Then there's these two results, also very interesting. Carefully show that this open problem of relating the Boltzmann equation to order equation, he has proved that, but he needs assumption on the limiting solution of the order equation are smooth, no shock wave. And 实现 could do it with one shock wave, okay, and nearby are smooth. But there's also this interesting thing he did recently, namely the interaction of a Boltzmann shock with the initial layer. So let me draw a picture of that. So suppose that you have the order equation, and you have a two-state minus and plus, which give out to a shock. Just this problem. You take initial data for the Boltzmann equation, which is Maxwellian with this state, Maxwellian with this state, and try to show that as the Coulomb number mean free pairs go to 0, the Boltzmann solution go to order solution. Just try that problem. It's a very difficult problem. Well, not very difficult. It's a hard problem because it involves the interaction of initial layer and the shock layer. Okay. I did this problem with David Hoff also in the 80s, and the Navier-Stokes also has its own initial layer and the shock layer interaction. And there's an idea is to make use of the Berger's equation, which, as we know, has an exact solution by Hofkohl transformation and so on. Okay, so let me move on. You would like to be able to show the solution of Boltzmann equation go to the solution of order equation with shock wave. Many of them. And there's only one result. And that is by Grimm in 1965 and one space dimension. Now, the analogous theorem on the level of PD would to show that if you put the viscosity to the hyperbolic conservation law and show that as this viscosity go to 0, the solution of this or go to the solution of this, the Grimm solution. And that was done by Bianchini and Bresson, an excellent result. However, Bianchini was visiting me in academia Sinica in Taipei for half a year, and where he came up with this center manifold coordinate or general Grimm scheme. And at that time, he thought that he could do it for the Navier-Stokes equation, the physical viscosity. But to this day, the physical viscosity, the Navier-Stokes, has so much coupling that there's no analysis for the zero dissipation limit. So this result may not have any bearing on the Boltzmann equation or the equation, but I thought I should mention it here. Now another thing about I want to mention at this point is that, well, the relation between the bottom equation and the order equation is very straightforward. As the Knudsen number of a mean free path go to 0, it should go to local Maxwellian outside the shock, and which means it should happen almost everywhere, and so on. It's just that it's very difficult to prove that thing. On the other hand, there's also the compressible Navier-Stokes equation, which has been derived. And that was derived by the Chapman-Enskog expansion. Now, I always thought Chapman-Enskog expansion is much smarter, and you can get the Navier-Stokes equation, where the Hilbert expansion will give you the order equation or hyperbolic equation with low order term. On the other hand, I have learned from the Kyoto school that this is somewhat misleading. Chapman-Enskog expansion expanded equation. Hilbert expansion expand the solution. And there's a big difference in that. When you expand the solution, already you are making a decision. You are making a decision on what the physical scenario you're talking about. Okay. And when you expand the equation, then you have to make another decision. There's certain universality about that equation, and which is not so in this rich situation. Okay, because the relation of bottom equation with fluid dynamic equation is very rich, and one should not make some hypothesis that there's certain universality. Bottom equation never stop Bernard. This is not a good assumption. Okay, depending on which physical scenario you choose to be in, you have a different set of PDE. Well, I'm just saying that the Hilbert 6 problem, right? We're talking about Hilbert 6 problem. Hilbert has a very straightforward way to do it, and that really has great strength. All right, so now if you look at the Chapman-Enskog expansion and how to derive compressible Navier-Stokes equation, you realize that there's certain assumption made in that derivation. Namely, the solution is rather smooth. And if there's a shock wave, now the Navier-Stokes equation has a viscosity, and viscosity is of the order of mean free path. And therefore, there's a very, if it is for small mean free path, there's a very steep shock wave. But yet, the Navier-Stokes equation was derived under the assumption of certain smoothness, which exclude the usefulness of this Navier-Stokes shock profile. So in the derivation from bottom equation, Navier-Stokes equation and order equation for small mean free path are actually equivalent physically. There are things of that which says that we need to go back to the first principle in formulating some of the problems relating to Hilbert 6 problem. I talk about the relationship with order and compressed Navier-Stokes equation. Perhaps it's more subtle and interesting from fluid dynamic point of view to look at the incompressible Navier-Stokes equation. And it is done the following way. First, you need the mean free path to be small, because if a mean free path is very large, it's like free molecular flow. And mean free path is very small, it's not very rarefied, then it becomes a continuum. And so you get the Navier-Stokes equation. So you take this k to be small. But you also need to wait for a long time, so you put a k there. And that is because for a short time, when you make a perturbation, there are, besides the vorticity, also there's a sound wave, which creates a shock wave, expansion wave, and so forth. Thus, acoustic wave, you want to wait long enough for it to go away, outside of your region, so that the motion can be modeled by incompressible Navier-Stokes equation. So you take K2 go to 0 and put this K there, which means for a long time. And you do the Hilbert expansion. Take G0, KG1, K squared G2, and so on. And remember, this is G. It's here. And you're going to let K go to 0. So on the level of kinetic theory, the relationship with the incompressible Navier-Stokes equation is the following. As K go to 0, you let have this G, which is of finite strength, but Kg will go to 0. And the solution F will go to a global Maxwellian. Okay, so on the level of incompressible Navier-Stokes equation, the kinetic theory part actually is very local. So you do expansion. You expand not only the distribution function, also expand the macroscopic variable. Oh, I'm going to supposed to start until 150. Until 2, okay. Okay. Then you do this Taylor expansion, collect all the K term, K square term, KQ term, and so on. At some point, you get the incompressible Navier-Stokes equation. Now, let me first say that that's an important result by Gors and Saint-Raymond to relate the Di-Perna-Lyon's weak solution to the solution of incompressible Navier-Stokes equation in the sense of the ray. And this is this important result is the end product of over 2 decades of work, starting with Corobado's idea that in this derivation we should use nothing but the conservation law and H0. Okay. And so that it was done, a great effort. However, if you look at this carefully, it's like this picture here, because Boltzmann equation, even in that limit, really cannot be closed by incompressible Navier-Stokes equation. It cannot. And that is because you have this subscript 1, which is the first term here. Okay. And the 2 means the coefficient of K2. And this is a zigzag here. The equation for V1 involves P2, not P1. If you go on with the P2, then you find out that in order to find the P2, it involves, of course, the next 3, and so on. But already in the case of P1, which one really should pair V1 with, the equation for P1 involves compressibility. So in other words, it is true that somewhere there's a form of incompressible Navier-Stokes equation surface up, but the pressure of the same level as V1 for the Navier-Stokes equation is under the compressibility effect. Now, another point here is that how do you solve a Navier-Stokes equation? How did Leray solve Navier-Stokes equation? Well, Leray showed that V1, here in this case, in this notation, V1 exists modular a gradient. And how about that gradient? How about that gradient? Well, that gradient, there's no estimate. And I have a see-through, I think, is Claude here? Claude. How many talks that François gave in Taipei in Simpa School? 8. Okay, and then I also heard Saint-Raymond give a series of 10 talks in Trieste. Yeah, In this talk, and I talked to Goris just this past weekend in Paris, and there's no estimate of P2. P2 has to turn out 1 over k and k go to 0. Okay. So this says that there's certain mystery about Navier-Stokes equation, more so than the Boltzmann equation. Because on the level of Boltzmann equation, you can compute the pressure. Okay. But on the level of Navier-Stokes equation, actually you cannot. And it's not clear whether this reduction clear up things or draw it into a deeper mystery. And in any case, much to think about in this process. So this is a concluding remark. I would say that in order to solve the Hilbert 6 problem, perhaps it's a good idea to go into back to Boltzmann in his spirit, and then do it with the spirit of Weierstrass and Hilbert. Thank you.
Thank you very much for this tremendous talk. Are there any questions?
Okay, can I make one or two comments since there are all these friends who I never dare to society put the thing on a clear ground. I can add some stupid or naive comment. And I have two, if I want to think about macroscopic or mesoscopic derivation from particle with first principle, I think I know two cases where the things are well done, as you said. First is when you have binary collision, which means it's very rarefied or it's very short range. And the other case is when you have a mean field limit, when one particle feels the action of all the other. To the best of my knowledge, for intermediate regime, I ask the question to the audience, there are a lot of things, but there is no complete mathematical derivation even for short time. Yes or no? The question for you, for Lelo, for... Probably.
Such as no.
I know, of course, the paper of, I own the old paper of Moret and several modern versions.
That's not the legal formal argument.
It's not only, I mean, it's formal as was our first paper of you and me on the boards, in the sense that there was no proof. But it's more formal in the sense that there is something which is added, a variational principle. And is there anything else in the tool on the shelves for that?
I guess we are in the business of welcoming problems, difficulty, and so on, right? So that's a good comment.
And
the less we know, the happier we are.
And the other question I have in mind is for the mean field. You go from reversible to reversible. That makes the thing easier. Mm-hmm. But then, if you look at the book in physics, or what Clément may talk about, Landau damping and things like that, or closure, you have a terrible hard time. Mm-hmm. If you look at your grad derivation, the entropy is at the first step. Mm-hmm. Then, I'm sorry for Loret, but everything becomes much easier after that, because you do have that. And maybe that's the last comment. Maybe that's in the book of Cercignani. He made several comments about the point where the irreversibility appears. Even the fact that it starts from initial data which are factorized, it's already putting the irreversibility, because in the future it's no more factorized.
Carl, that's a very now that you mentioned this one, I want to highlight this book, Molecular Gas Dynamics by Yoshio Sone. This is a book for mathematician.
Yeah.
Okay, thank you.
Any other questions? Another question?
Vas-y, Clément, yeah.
And still factorization asymptotically preserved.
Yeah.
For a small time.
No, you have other point of view with.
But in our theory, it does nothing like this, which is worse in a way. If you factorize, it means you close something at the limit. You have laws on the limit, which is the Boltzmann equation.
Yeah,
This is factorization really means on the one marginal you close a PD at the limit, and it's proved in Stanford in a very short time.
and that's true.
I have a question related to the part one, the last open question about correlated systems. Has anybody considered the I will call n-squared limit? Instead of n d squared go to 0, equal constant, you consider n dq equal to constant.
Oh, that's definitely outside of the Boltzmann thing.
Well,
yeah.
it is still
Yeah.
closely. If you want to consider the interaction, non-zero, the first step is outside of ideal gas. If you take n d squared equal to constant, that's still ideal gas. So those, in a thermodynamic limit. So the only step, you don't have to consider long range and everything. All you need to do is, the first step is n-squared type of thing.
No, NDQ fixed is bad. It definitely is outside of this verified gas. Yeah, that definitely is outside. Oh, by the way, now that you ask this question, this lattice Boltzmann equation thing, which is an important subject, and some of this analysis that I mentioned in terms of this thing here. That would be a subject which is really is also part of kinetic theory, and to really study under what exactly precise under what the situation where the lattice Boltzmann equation actually solve the Navier-Stokes equation. Because I'm proposing that Navier-Stokes equation is more mysterious than Boltzmann equation. Now you are trying to solve Navier-Stokes using Boltzmann, right? So there's a much to think of it. Okay, I get this stuff here.
Okay.
I suggest we, I don't know, take some 2 minutes break before we swap over to our second speaker.
Okay, thank you.
And it's very good to have all the discussions. Maybe you could remind the ideas, keep on talking about it.
Okay.
So let's thank Tai-Ping Liu again.